All right, here we are in our last of the lectures on non-deductive reasoning. We're talking now about Introduction to Statistical Reasoning. This is a very broad area, and you can take entire courses on statistics, many of them, in fact. And I hope that you will, because it's a really important area of human endeavor. It's really crucial to understanding science and even politics to have a good idea about statistics. So we're just going to be barely scratching the surface here in these 8 slides, so I'm not nearly going to get to the bottom of things, but I want to just explain a couple of things from a philosophical point of view. Now, the kind of reasoning that I want to emphasize today is reasoning from a sample to an ensemble or a population. So a sample is a subset of a total population. And it's very common to do these kinds of inferences where you, for example, poll 1,000 Americans, figure out what percentage of them approve of the president's performance or something like that, and then you make an inference about the total percentage of people in the entire American population who approve of the president's performance. That's an example of reasoning from a sample, a small subset of a total population, to something being true or probable about the ensemble. Now, why does it end up being just probable? Well, because the sample might not be a good reflection of the total population. You can never be perfectly sure that your sample is a perfect reflection of the overall population until your sample size equals your population size. Right? So that's when we get certainty, but until we get to that, we're always dealing with a little bit of a guess, and so that's why our conclusions are probable. Now, what statistics is able to do is to quantify the amount of uncertainty that's in these kinds of inferences, and I just want to explain to you the very basics of how that works. So I mentioned political polls, lots of other kinds of studies that do sample to population inference, environmental studies, for example, drug trials sometimes do this as well. So this is an important kind of statistical reasoning, but don't forget it isn't the only kind. There are other kinds as well. Now, the idea of a sample to population inference is based on a Gaussian or normal distribution. Most characteristics in nature are distributed according to this curve, right, where you've got a peak near the average value or at the average value, and then kind of a bell-shaped curve where there are some at either end, but not nearly as many as there are near the middle. This is the chart that I used at the beginning of the course to say that this is what a standard grade distribution looks like in most classes, but it's not the one that we get for logic. But if you replace the grades along the bottom with, say, the height of a corn plant, you'll find that there are some very, very short corn plants, there are some that are very tall, but most of them are pretty close to the middle value, the average. Okay, so we use that basic idea in a sample to population inference by taking a subset of the total population and creating a graph of that population's distribution of whatever characteristic we're looking at. And then we can make an inference that the total population resembles the sample population. Right? So it's the strength of that resemblance relation that's really in question here. And the various statistical techniques like increasing sample size, making sure that your sample is randomly selected and not skewed, those are all attempts to try to make sure that the sample is similar enough to the total population that the inference is reliable. Okay, so I mentioned the idea of sample size, and generally the larger the sample size, the better the inference that you're going to make. If you only interviewed 10 Americans about the president, you might have accidentally interviewed 10 Democrats or accidentally interviewed 10 Republicans, and then the result won't represent the entire population very accurately. So what you want is to have a random sample that is like the population. We call that a representative sample. And it's really hard to be sure that in any given case you have a representative sample, but there are statistical techniques that you can use to try to make it as likely as possible that you have that sort of sample, okay, that one that is resembling the total population, one that's representative of the overall population. Now, if you think about a political poll like presidential approval ratings or something like that, or the percentage of people who are going to vote for one candidate rather than another, you'll see these reported in the newspaper in this kind of way. Right? There'll be some value, say 45%, just pick the value, plus or minus some other percentage, and then a sort of a caveat that says 19 times out of 20 or whatever they say. So what does this mean? Well, this is telling us that they've done an experiment or an observation which found that the rate in the sample, in this example, was 45%. And now they're making an inference from the sample rate of 45% to the population rate. And the claim is that the population rate will be between 40 and 50%, 95% of the time. Right? So we'll talk about each of the parts of that in a minute, but it's important to recognize that every sample to population inference, it has to be expressed this way, or else it's a bad report, or you shouldn't trust it. Okay? So if anybody tells you that the president's approval rating is 45%, they're either just giving you a shorthand, or they don't really know about statistics. So if the approval rating is 45%, it's 45% plus or minus the thing that we call the margin of error. And then there's a confidence level that goes along with that. Now what that confidence level means is that if you look at the very long run of experiments of a similar kind, what you would find is that if you have a sample of that size and that kind, 95% of the time, the true value for the population will fall within the range that's defined by the margin of error. If you need to repeat that, go ahead. The idea is that there's no guarantee that the population value matches the sample value, even within just the margin of error. But you can statistically calculate that in some certain number of percentage of runs of this kind of observation, that there'll be a percentage of times that the population rate does fall within the margin of error. Now there's a set of complicated equations that tell you how big the margin of error has to be given your population size, your sample size, and the confidence level that you choose. We won't get into any of that. That's something you'd study in a statistics class, but just know that there is that relationship that if you choose a higher confidence level, for example, instead of a 95% confidence level, the 99% confidence level, then typically what that means is that you either need to increase your sample size a lot, or you have to really increase the size of your margin of error, thereby increasing the confidence interval. That's the name for that range between 40 and 50 in this example. All right, so if you decrease your confidence level, if you're willing to say that, well, it's only going to get the right value 50% of the time, then you might have a very, very narrow margin of error. So there's always a trade-off then between these things. And that's partly what statistics is about, is trying to figure out what that relationship is and what's the best way to do it. Now, what you find in most fields, like the social sciences or other fields that use statistics, is that they have a sort of ordinary expectation that statistics in their field will have a certain confidence level. So in psychology, the typical confidence level is the 95% level. That's also what you see in political polling and things like that. Usually they say 19 times out of 20. That's the same as saying 95%. In other fields, though, they have higher standards. In medicine, for example, they sometimes want to use the 99% confidence level. In particle physics, they use 5 sigma, which is a really very high standard. They actually want to have it to within 0.99999. They want to have a 0.99999 chance. In other words, a 99.999% chance of the measurement being accurate. That's an extreme case, right? What that means is that the margin of error has to be larger, or the number of runs, or the size of your sample has to be much, much larger. So this is all just to say that different disciplines have different standards for the normal confidence level. So if you're used to the 95% confidence level and you see something that's 75%, you might think that's terrible statistics, but you have to look at what the disciplinary expectations are to see whether that's really normal or not for that particular field. All right, so The 45% then will be the rate of whatever the characteristic is that you're measuring in your sample. The margin of error is calculated from the statistical situation, and that is based on choosing your confidence level. Okay, so the confidence interval is the range of values that's defined by the rate plus the margin of error. Notice plus or minus means that you go below and above that rate. And then what you're saying is that the true value for the population falls within that range, that confidence interval. And then according to the confidence level, whatever the chances of that occurring. Okay, so if you decrease the size of your margin of error, that typically decreases your confidence. If you have a very small margin of error, it's less likely that the true value for the population falls within the confidence interval. And so the same thing goes the other way around. If you choose a higher confidence level, then you're going to have a wider confidence interval. Now, ideally, what we want is to have a very small margin of error and a very high confidence level. You could describe those as having high precision and high accuracy. If you can achieve that, like they do for many results in particle physics, then that's an extremely robust, strong result. Okay, that's kind of the gold standard. That's the thing we're looking for. But that's very difficult to get, very difficult to do. And that's partly because of a trade-off between what's intellectually best and what's practical or expedient or you can afford to do. Right? If you want to poll the American public to find out their voting tendencies, you have to have an awful lot of money to call a big number of them. Right? If you just want to call 1,000, you probably need a few days worth of work for a few people, and so that's an expense, certainly. If you want to double the number of people that you call, well, you're doubling your expense. So that expense and the time that it takes to do these kinds of studies, those are costs that you have to trade off against the accuracy and precision of the information that you're able to get. Now, an important thing to recognize about margins of error and the confidence interval is that if you have two polls, for example, or any two measurements in statistics, where their confidence intervals overlap, right, that one measurement falls within the margin of error of another one, then what you have to say is that those two measurements are not different. Technically, we could say they're empirically indistinguishable, right? We can't tell them apart. So if the two polls seem to give you different results, one says 43 and one says 45, but they both have a plus or minus 5% margin of error, well, really, those two polls are telling you the same thing, right? They're overlapping. So they can't be said to be different results. It's a really important concept to grasp when you're trying to interpret statistical reports. I'm going to leave it here. There's obviously way more than can be said about statistics, but we don't have time for it in our course. Just wanted to give you just a fundamental idea of what's going on in statistics and how it works. If you can wrap your head around that, then you'll be able to master reading the polls for the upcoming national election. By the way, there's a really great website called 538 that is run by Nate Silver. He's a pretty famous statistician. Used to work for the New York Times. Now he has his own company, 538. And in addition to doing great poll analysis, he also has some parts of his website where he explains statistics in a really nice way. So that's one place to go if you want more knowledge in this field. And Khan Academy also does a great job with this. Okay, so this is the last lecture for this topic. Good luck, and let me know if you have any questions.